In this video, we're going to be going over worksheet number 3 and worksheet number 4. Um, for worksheet number 3, you guys were asked to look at this modified Atwood's machine, which has a heavy block on the left side and a small 2 kilogram block on the right side. They tell you that the big block is 5 kilograms. They also tell you that this is a frictionless surface. We're always going to ignore the forced friction here. And then they tell you that the mass of the pulley is non-existent, right? Which we know is not realistic, but we'll go with it. So the first thing I ask you to do is to draw a force diagram for each of them. So I have my force diagram for the block A on the left here and a force diagram for block B on the right. I was able to easily figure out the force of gravity. It's a 5 kilogram block, so it's 50 newtons down. And then on the block B, it was force gravity 20 because it's a 2 kilogram block, so 2 times 10 is your 20 newtons of force gravity down. Now, the reason that I put my net force as going down on block A was because I think most of you would be able to figure out if I have a heavy block on the left side, block B would go up and block A would go down. So obviously A has to accelerate down, so the net force must be going down on block A and up on block B. That means the force tension going up on block A is going to be less than the force gravity on block A. And then on block B, the force tension must be greater than its force gravity, otherwise it would not accelerate in this way. So we have our force diagrams. And then the final thing we do need to really talk about with these is that the force tensions, right? The force tension is always going to be equal throughout a rope. So if I know the force tension on this left side, that will be equal to the force tension on the right side. So there's my force diagrams, but what is the acceleration of the system when the blocks are released? When I let them go, what is their acceleration going to be? We know it's going to be down for block A and up for block B, right? And it's easy to get a little bit confused when we have it set up like this, where both block A and block B would be being pulled down by gravity, but really saying that their gravities or that their forces are pulling in the same direction is inaccurate, right? Block A is not pulling in the same direction as block B. In this case, the pulley kind of makes it seem that they are pulling in opposite directions. So what I did up here on this little diagram is I drew what could be a not necessarily more accurate way of representing this, right? I think it's actually less accurate, but I think it's easier to see what our net force on this system would be when I draw it like this, because then it makes it easy to see, oh, the force gravity on A is going to the hypothetical left, and then the force gravity on block B is going to the hypothetical right, and they're pulling in opposite directions. But that makes it really easy to tell, oh, the net force on this system must be 30 newtons, and it's going in the direction of A, so it's 30 newtons down or 30 newtons to the left. All right. Once you have that net force, it makes it really easy to find the acceleration. We just need to use F equals ma. Force divided by mass will tell us the acceleration then. So our net force of 30. And then if we're looking at the net force on the system and the acceleration of the system, we need to take the mass of the system. So not 5 kilograms, not 2 kilograms, we need 7 kilograms. So our net force of the system is 30 divided by the mass of the system, all the blocks together, 7 kilograms, and that should be about 4.3 meters per second squared. Now what's really important here is to remember that if you have one part of the system as accelerating at 4.3 meters per second squared, all parts of the system are going to be accelerating in that same direction, right? If you are in a car and the car is going at 60 miles per hour, you are also going 60 miles per hour, right? So it's the same thought process here. So the whole system is accelerating at 4.3 meters per second squared. So we know that block A and block B individually are also accelerating at that amount. Now, once you have the acceleration, it makes it easy to find the net force. And once we have the net force and the force gravity, we can figure out what the force is going up. Right? From here, it's pretty much just the same as we did on worksheet number 1 and worksheet number 2, where we need to figure out how much force is pulling up or how much force is pushing up. And we know the force net and we know the force gravity. So what's our net force on block A? Force net equals mass times acceleration. 5 kilograms times 4.3 meters per second squared, our acceleration. you get a net force of 21.5 newtons down. So if we have 21.5 as our net force, and force gravity is 50 newtons, and you can tell the force gravity wins by 21.5, then that force tension must be 28.5, right? For block B, then, we can confirm that our force tension is 28.5, or roughly that, by going through finding the net force of this. Again, F equals ma, our mass of 2 kilograms, times our acceleration, again, 4.3. So on the right, on block B, we can figure out that the net force is 8.6 newtons. So if our net force is 8.6 and our gravity is down 20 newtons, in other words, 20 newtons down, but that loses by 8.6, then we know our force tension must be 28.6, which is within a rounding error of 28.5, right? We're 0.1 off. I would say that if we hadn't rounded our acceleration, that we would probably get the correct answer, or the answer that is, perfectly equal. But 28.5, 28.6 are close enough for this case that I would say we did that right. Again, we did not need to calculate the second force tension because we knew they should be equal. Question number 4, or worksheet number 4. This should actually be a little bit simpler once you go through worksheet number 3. We do need to pretend that the force of gravity is pulling block B straight to the right instead of straight down. But again, that's just making it easier. But what we had to do first is draw a force diagram. For the block that is on the table, sliding on the table, and they tell you that it is not frictionless, and actually they ask you to calculate friction here, so you know you need it. It's force friction pulling to the left. Force tension is pulling to the right. Force normal is pushing up with 40 newtons because force gravity is 40 newtons down because they tell you it's a 4 kilogram block. I know my force tension must be greater than my force friction because it's accelerating to the right. So my net force is also to the right on that 4 kilogram block. And then the force gravity is pulling down on the 1 kilogram block. And I know my net force is going to be down on that because the force of gravity should be greater than force tension because this will drop down, it will accelerate down. So for this one, they don't even ask you to calculate force tension. If you did that, awesome, but you didn't have to. For this one, all they ask for is the acceleration. So I had to draw my coefficient, or I had to figure out the coefficient of friction. I had to figure out how much the value for friction is. And then from there, the acceleration should be pretty straightforward. So the force of friction is equal to the coefficient of friction times the normal force. Coefficient of friction, they told you, was 0.2. The normal force here, we calculated that earlier, was 40 newtons. 0.2 times 40, your force friction going back on this object is 8 newtons. So if we know it's 8 newtons going to the left, and we're going to pretend that instead of pulling this block down, the force of gravity pulls it to the right, then we know the force of gravity is 10 to the right, 10 to the right, 8 to the left. You know the 10 to the right wins, and it wins by 2 newtons. So there's our net force is 2. Our net force divided by the mass of the system will tell you 2 newtons divided by 5 kilograms, and you get 0.4 meters per second squared is your acceleration. Now, if you're an honors student, you then also had to do question number 2 on here. A block weighing 300 newtons is moved at a constant speed over a horizontal surface by a force of 50 newtons applied parallel to the surface. So they tell you it's a 300 Newton block. In other words, they're telling you the force gravity is 300 newtons. If you know the force gravity is 300 and it's moving at a constant speed, you know the force normal also has to be 300. They tell you the force pushing forward is 50. And again, constant speed, so I know the force friction going back on the object has to also be 50. So I'm going to rearrange my force friction formula to get force friction equals the coefficient of friction times the normal force, and then force friction divided by your force normal will give you your coefficient of friction. My force friction was 50. My force normal was 300. So my coefficient of friction is 0.16 repeating. So what would that acceleration be if the coefficient of friction was 0? Now this seems like a complicated problem, but it's really not. All you have to do is, if you have no coefficient of friction, then you have no friction, right? So if we have no friction here, my net force then is just 50 newtons to the right. If the force push is not being opposed at all, divided by the mass of our object. In this case, we knew the mass of the object was 30, because if our force gravity is 300 down, then your kilograms is just, you divide by 10 on your force gravity. 300 divided by 10, you get 30 kilograms. So 50 divided by 30, you get 1.6 repeating as your acceleration here. And then on the right side, I just kind of proved to you guys that it was 30 kilograms by showing more of my work. But again, 1.6 kilogram or 1.6 meters per second squared is your acceleration of the block if you have no friction. Please let me know if you guys have any questions as we went through this. And again, you can always pause these videos and rewatch them. Have a good day, guys.